I've heard it said that if you were to only remember one thing about basic circuits, it would be node voltage, which has the implication that mesh current, or I'll say it again, just in case I said it bad the first time, mesh current, um, as a systematic method, is slightly less important than node voltage. And that might be implied by how we often draw circuit diagrams with multiple grounds to obscure our meshes. But even still, if you ever learn something about transistor amplifiers, you'll find that usually how we solve those is with two loops, one for the base and one for the collector. And so mesh current does not go away. If you continue on in circuits, mesh current will continue to be used. So even though it's slightly less important than node voltage, it's still important, although maybe slightly harder to teach. So what is mesh current? Well, I'm going to draw a couple more loops here. It's very difficult to describe the motivation for mesh currents off of first principle. But I guess what I could say is node voltage is writing Kirchhoff's current law in terms of voltages and in defining a voltage for each node using some sort of referencing. So you would think maybe there's some sort of analogous method you could use that where you write maybe Kirchhoff's voltage law in terms of currents, and you somehow define a scalar current for each of something, whatever that is. And so that may help you think of mesh current. Maybe just as an academic fun exercise, not really knowing what it would be useful for once you figured out what it is. So a mesh current is defining a quote-unquote fictitious current around a loop that is a subloop of some larger circuit. And it's a mesh if and only if it does not contain any currents within it. So a mesh is like this. If you can subdivide a mesh into smaller loops, it's not a mesh. Now, what you notice right away with that is that what the meshes are for a circuit will depend on how you've drawn the circuit. I could draw the circuit a different way, where I take, say, these two components, and instead of drawing them the way I did, I'll pick like a light gray or something here, connected them like this, and not there. And then this would be a mesh, and then this would not be a mesh, because I've mapped this loop, which has no subloops, to this loop, which has many subloops, and this outer loop, which has many subloops, to now this loop, which has no subloops. So I'll undo that. And this is unlike node voltages, where what the nodes are is independent on how you've drawn the circuit. I rearrange it, the nodes are still going to be the same nodes, and my node equations are going to still be the same node equations. So I say, okay, there's a current going like this. Well, but what about this current? And down this branch, what about that current? And what about this current? Well, I say, well, Kirchhoff's current law needs to be true at, going back to like an orange, at this node. So some of the currents coming into that node has to be some of the currents going out. If I define a current, I can define a current like this, and now the sum of the currents going out is equal to the sum of the currents going in. Because these two go in, and then they both come out. Likewise, I could define it this way. And so if I continue this and write an entire new mesh current up here on this loop, and I say that the current going through this component is defined this way is I1 minus I2, then I've created a situation where Kirchhoff's current law is satisfied right here. And if I do that here, I can see that, like, by the way I've defined these currents, the way I've set this up, automatically Kirchhoff's current law is satisfied at each at each node. This is very similar to how, if you define, because of Kirchhoff's voltage law, I can define scalar voltages at each node. And as we saw from the node voltage systematic method, satisfying the Kirchhoff's current law forces the mesh currents to be true. I'm going to speak again. The node equations to be true. And because the node equations have the same amount of unknowns as equations, they, for one definition of ground, specify unique node voltages, which, with any specification of a ground, gives unique voltages across each individual component. So the solution to a resistive network is unique. So if I find some sort of scheme that satisfies Kirchhoff's current law at every node, it's must then produce the correct answer for the individual voltages and currents through each individual component. So this current if I define it, say, what's this current in terms of the mesh currents? It's I1 minus I2. So the current through each individual component is the difference of two mesh currents on the adjoining meshes, in the same way that the voltage across a component is the difference of the voltages between the two nodes that component joins. And this current going defined this way is I2 minus I3. The plus sign always goes with the mesh current that's going along with the current you're defining, and the minus sign with the mesh current that goes against. So we define these mesh currents. You don't have to define a ground. If you want something that seems analogous to a ground but for mesh currents, is actually, I would call that the outside loop. So the outside perimeter of the entire circuit. But just as we don't do Kirchhoff's current law at ground, we don't do Kirchhoff's voltage law around this loop. So very analogously to node voltage, just as in node voltage we write down node equations where we write down Kirchhoff's current law in terms of node voltages, here we write down mesh equations, which are Kirchhoff's voltage law in terms of the mesh currents. And just like how we were writing down a current law in terms of voltages, so we need to use Ohm's law, we're writing down a voltage law in terms of current, so we need to use Ohm's law. Except this time, instead of dividing by resistance, we multiply resistance, because V equals I times R. And then we solve the mesh equations for the mesh currents. Just like in node voltage, where if we're given an independent current source, then that just specifies a current within the Kirchhoff's current law. Independent voltage sources just fix a voltage within Kirchhoff's voltage law. And just like in node voltage, where if we had a voltage source that was abutting the ground, it would just specify a node voltage automatically. We didn't have to solve for it. current sources, dependent or independent, although independent entangle things more, on the outside, just straight up specify mesh currents so we don't have to solve for them. And then, similarly to in no voltage, if we have a voltage source spans between two nodes that neither of them are the ground, we have to use a supernode. Well, if we have a current source that's between two meshes, we use a super mesh. So going back to voltage sources, fixing voltages, that could be kind of somewhat confusing. So say I have a voltage source. Maybe I wanted to make the polarity different. 1 volt, and then R1, R2, and R3. I always like to define my mesh currents going clockwise. You don't have to, you can define them going counterclockwise, but I always make them going clockwise. Then I consider a positive voltage, voltages where if I were to have a resistor there, the voltage would follow voltage drop. So according to passive conventions, I don't have to do a sign switch in the Ohm's law. So for all my resistors, I say a positive voltage is such that that voltage follows the voltage drop. The mesh current follows the voltage drop. And remember, for Kirchhoff's voltage law, for all the voltages to be lined up the same way. So remember Kirchhoff's current law, it's like they're all of them going in equals 0, all of them going out equals 0. With Kirchhoff's voltage law, all the voltages add up to 0, but they have to be oriented the correct way for that to happen. If we define a current all the way around a loop, as long as if that current were to follow voltage drop for all the voltages around the loop, then those voltages would be lined up correctly for Kirchhoff's voltage law to work. And that is, plus and plus minus. So plus minus, plus minus, plus minus. So this way of defining things is in agreement with that. This makes it such that for the voltage source, it should also be defined plus minus with the plus upstream and the minus downstream. And in this particular case, the polarity is reverse of that, so I need a minus sign. So this brings about a certain rule that I like to follow, and many other people do as well, that if you're doing, as you write down the Kirchhoff's voltage law for mesh currents, if you encounter a voltage source, the sign you hit first is the sign you have to put in front of the term for that voltage source. Because for all the resistors, you hit the plus first. They're all plus. And then the source, in this case, would be a minus sign because I hit the minus first as I go around the direction that the mesh current is defined, which in this case is clockwise again. So the node equation for this would look like, let's call this mesh current I1, R1 I1 plus R2 I1 plus R3 I1 minus 1 volt is equal to 0. And that would mean that I1 is equal to that 1 volt divided by the sum of those resistances, which makes sense because they're resistors in series. The equivalent resistance of them is them added together. Okay, let's go on to the example problems. There are fewer of which this time in comparison to node voltage because I just couldn't come up with as many. So here's the first one. Pretty simple. So I'll define my mesh currents like I like, clockwise. And write down my 3 mesh equations. So starting with the first one, I have a plus 5 because I hit the plus first as I go around clockwise. Plus 6i1 minus I3. I multiply by resistances now because voltage. I'm adding voltages, and voltages is a resistance times current. Something that makes designing mesh current problems maybe a little easier than designing no voltage problems. Plus 12 I1 minus I2. Then I write down my second mesh. I'll clean that up a little bit here. This equals 0. So 18 I1 minus 6 minus 12 more is minus 18. I don't know what I'm... Inevitably, these kind of things will happen. Minus 12 I2 minus 6 I3 is equal to minus 5, moving it over to the right side. So that's equation 1. So equation 2, we do this mesh. So 12 I2 minus I1 for this resistor, plus 3 I2 minus I3. The mesh you're on is always the one that comes first because the second mesh, the mesh I'm on minus the mesh current on the adjoining meshes. Again, I hit a minus sign. I hit a minus sign, so that's minus 7 is equal to 0. So then 15 I2 minus 12 I1 minus 3 I3 is equal to positive 7. And that's my second equation. Third mesh, 6 I3 minus I1 plus 1 I3 plus 3 I3 minus I2 equals 0. So that's minus 6 I1 minus 3 I2 plus 10 I3 equals 0. And I'll put these into a matrix. So I make this box. 18 minus 12 minus 6. And then I always mess up. I tend to mess up the orders of these if I don't write them in order beforehand. But anyway, minus 12, 15 minus 3, and then minus 6 minus 3, 10, and then I1, I2, I3 is equal to minus 5, 7, 0. And I have a good check here, and then all my I just have resistors and voltage sources, so I should see that these down the line diagonal are positive. So at least I got the middle ones right. Hope I didn't mix up the other ones. And on the same theme as my node voltage lecture, I like to use Cramer's rule. So first take the derivative, not the derivative, the determinant of the original coefficient matrix. So this is a lot of math. 18 multiplied by this minor, which is 150, minus 9, which is 141, plus 12. It's minus 12, which is plus 12, times this minor, which is minus 120, minus 18 more, so minus 138. Lastly, plus this minus 6, because that's a plus because it's in the corner. This minor, which is 36 minus 90. So plus 90. So 36 plus 90, which is 106. And this is an absolute nightmare. So I'm going to type this into Python. And I'm going to have to edit this afterward to edit out the time for which I am doing this. Okay, finish typing that in, and it comes out to be 126. And yeah, that seems about right, because you have like 18 times 12 minus 6 times things that are 100 a piece. So you have 18 minus 12 minus 6 on things order 100. Okay, so then D1 is the determinant of, if I put this into the first column, my sign 7, 0, minus 12, 15, minus 3, minus 6, minus 3, 10. And I'm going to evaluate that, I'll be back. And that comes out to be 261. And then I'll do D2 and D3. Okay, so D2 I believe is 318. And D3 is 252. Now this all seemed kind of silly. You think, well, I might as well have just did a lin solve using NumPy, as opposed to doing individual determinants in NumPy and then having to divide them. And yeah, you're right. I don't know what I was doing. But if this were a test, though, I wouldn't have NumPy. And so I would have to do this, but I'd have to actually grind out the individual determinants, and the probability that I would make some dumb mistake somewhere would be extremely high. That's the way it goes. It looks like I2 and I3 reduce. No, I2 reduces. What was I writing here? What even? All three of these are wrong. I don't know what I was writing. I'll just leave that junk in there. 261 over 126, 318 over 126, 252 over 126. I know this one is 2. So that one reduces. I don't know about the other ones. I could check them. So what was the first one? 261 over 126. Nope, that one is like a 7 or something, so that one doesn't reduce well. Let's see. Yeah, okay. How about 11? Close. 13. We're trying to prime factorize 261. Up to 23 still doesn't prime factor. How about just 3? Okay. So, is 126 divisible by 3? Yes, it is. So this is 87 over 42. This is 106 over 42. 87 is divisible by 3 again, I believe, so that's 29 over 14. This 106 is not, but they're divisible by 2, so that's 53 over 21. Okay. 29 is prime. I believe 53 is also prime. So I could plug those in and check. I'll check equation 3 at least. So that would be minus 6 times 29 over 14 minus 3 times 53 over 21 plus 20 equals 0. So minus 3 over 7 times 29 minus 53 over 7, okay, plus 20 equals 0. So 3 times 29 is 87. We already went through that. So minus 87 minus 53 more is minus 140 over 7 plus 20. So that checks. So you would do that on the test if you had enough time left to check. And then I'll leave the rest, and hopefully these end up being right in the end. Sorry that took so long, especially to me, because I'm going to have to edit things in there. But let's go on to the next example problem. So this was a little bit simpler because there's only 2 meshes. I start with the call this one I1, call this I2. Write down my mesh equations. So 50 I1 plus 50 more I1 plus 20 I1 minus 1 plus 2 plus 100 I1 minus I2 equals 0. As you would notice, you could just combine these 3 resistors in series beforehand. Notice how if rearranging the position of the resistors and this voltage source does not change the mesh equation, therefore it doesn't change the solution to what you get for the mesh currents. It will change, of course, the node voltages because it rearranges the nodes. But it won't change the voltage drop across each individual component. So you can always rearrange the voltages afterward. So this is 225 I1 minus 100 I2. This is positive 1, so it's equal to negative minus 1 on this side. So that's the first equation. Second mesh equation. So 30 I2 plus 4 minus 100 I2 minus I1 minus 2 equals 0. So that's 100 I. Why did I put a minus here? No idea. Positive 1 minus 100 I1 plus 130 I2. That's positive 2, so it's equal to minus 2 on this side. Cool. I'm going to look at this again. So 225, it have 50 plus 50, it's plus 100 plus 25 is 225. Minus 100, this is conjoining on the other side. Plus all the voltage, which would be a minus 1 and a plus 1, plus 2, which is plus 1, move to the other side, minus 1. For this equation, the sum of all the resistances are 130. The other side is 100, and the voltages are plus 4 and minus 2, which is positive 4 and minus 2 on the other side. Okay, so if I have a 2 by 2, my favorite way of solving it is just inverting the matrix. So that's 1 over the determinant of the matrix, which is 225 times 130 minus 1 E4. And then this diagonal, you switch places. The minus diagonal, you just put on minus signs. And then we multiply this by the other side with minus 1 and minus 2. I'll do the matrix multiply first. So 1 over this nonsense, which is 22500 plus 6750, which is 29250, minus 1 E4, which is 19250. Great. 130 minus 130 minus 200 more is minus 330, and then minus 100 minus 550 more is minus 650. So this ends up being minus 33 over 1925 divided by minus 65 over 1925. And then you go, okay, is 1925 divisible by 11 or 3? And it's not divisible by 3 quite, but it is divisible by 11. So this is equal to minus 3 over 175. And this down here, 65 is 13, so minus 13 over 385. I believe that should be correct. Let me check and make sure. 1925 divided by what was it? 5 is 385. Good. Is 385 divisible by 13? No, it's not. So that's the best I can do for that. And then I want to plug these two things in and check. So let's ignore these 1925s for now and say, okay, minus 300 plus, oh, I have to redo that multiplication. Goodness gracious. We're just going to hope, oh dear. Well, I have to check it, so I'm going to check it. I'm going to stop recording and check it and then try again. So I checked these, and I found out that I made the following mistake. I multiplied 225 by 2 and wrote 550 instead of 450. So this should be, if I had 100, I should get only 550. So this up top here should only be a 55. And then this should end up being an 11. And then if I check and see if 385 is divisible by 11, it is. And so I2 should end up being, so I'll have I1 is equal to minus 3 1/75, and I2 is equal to minus 1 over 35. Oops. Moving on to the next example problem. Let's see what it is. Okay. I marked out a voltage here. I presume that means that I want to find it. I'll start by writing mesh equations. Here, of course, you can see we need to use a super mesh. Or, if we don't like the idea of a super mesh, we can just rearrange these two parallel elements like so. And that will not change the voltage that I'm trying to find, because I'm changing a disjoint part of the circuit here. I can make this two-terminal network, into this two-terminal network. It's the same two-terminal network. And then I have a mesh current already found. I will, though, however, like in a silly way, use a super mesh anyway, just to demonstrate how to do a super mesh and for no other reason. If I were just doing this for my own good, and I wasn't doing a lecture and I wasn't trying to demonstrate how to use a super mesh, I would just rearrange it such that that current source is on the outside. That's something you cannot always do. So we have our super mesh I1, and then this mesh, well, nope, that's not how you do that. I don't know what I was. Mental lapse. I1, I2, I3. Okay, so I1 equation. Well, first the super mesh. So just like any other mesh, we're going to go around this clockwise. 15 I1, and then keep going, plus 10 I2, because that's the mesh, plus 5, because we hit the plus terminal first as we go around clockwise. And that's it. We've gotten all three components. We've gotten all the way around the super mesh, equals 0. And then the current source in the middle determines our second relationship between I1 and I2. That is minus I1 plus I2 equals 1. And it's minus I1 because I1 is going contrary to how the current source is defined, and I2 is going with it. So I2 has a plus. And then we have our third mesh over here. So that's minus 5 plus 20 I3 plus 10 I3 is equal to 0. And because the component that joins the mesh 2 and mesh 3 is a voltage source, I don't have any coupling here, and so my I3 is real easy to find. It's just equal to 5 over 30, which is equal to 1/6 of an amp. So then I just have to solve a 2 by 2 here. So I'll just solve the 2 by 2. An easy substitution looks like I2 is equal to 1 plus I1. So 15 I1 plus 10 times 1 plus I1 plus 5 equals 0. So 25 I1 plus 15 equals 0. So I1 is equal to minus 3/5. And then I2 is equal to 2/5. And these all have units. If you don't put your units on the exam, you often will lose a point depending on how your professor is. So technically I should have put units there, and I should have put units there. Okay. So that was a quick one, and that's that. The voltage here that I wanted to find is just 10 ohms times I2. So V find is 4 volts. Hopefully I didn't make a silly mistake somewhere in there. I'll just have to hope. If someone actually watches this, this will be on YouTube, and they can watch it, and they can write in the comments that there's a mistake I didn't catch. And that will be embarrassing. Okay, here's one where the mesh currents are already predefined for some reason. Oh yeah, it's this one. Okay. So I'm giving myself mesh currents and trying to find the gains on the dependent sources. Excuse me. That are self-consistent with the mesh currents given. I just ate, so my voice is going to start sounding like I'm talking my dinner back up. Okay, so we just like before, else we write down the mesh equations. We don't need to write a mesh equation for I1 because it's given because I have a current source hanging around here on the outside. So that will tell me I1 without having to do anything. And I defined I1 the same way as I made this current source. So at least in that way, I don't have any conflicts of the given information. Again, that's really easy to do when you're when you're trying to make a circuit problem. It's really complicated. So write down the other mesh equations. So first of all, they have to be a super mesh because there's a current source between them. So we'll write the super mesh one first. So 30I3 minus AVA plus 10I3 plus 5 plus 10I2 minus I1 equals 0. Now VA, did I not put it on this? I'm probably going to have to stop recording and see where that was supposed to be. Okay, sorry, what I would have wanted would be for the VA to be across the 10 ohm and for IB to be coming in here. Okay. It's important when you define your dependent current sources or voltage sources what they're going to depend on. So then we can write VA in terms of mesh currents. So 30I3 minus A times I1 is going with passive convention. So it's I1 minus I2 multiplied by 10 plus 10I3 plus 5 plus 10I2 minus 10I1 equals 0. Trying to combine like terms here, so you have a 30I3, a 10I3, and you should have a 10I, yeah, just a 30I3 and a 10I3, so 40I3. We have a plus 10AI2 and a 10I2, so that's 10A plus 1 I2. We have a minus 10 I1 and a minus A I1 times 10, so that's minus 10 A plus 1 I1. And then we have 5 here that becomes a minus 5 on the other side. Then we have the super mesh, which is just I3 minus I2, or the other super mesh relationship, is equal to BIB, where IB, better keep it on the screen here, is I1 minus I3. So then 2I3 was a B here. Okay, so it's not 2I3. 1 plus B I3 plus I2, it's a minus sign, plus minus B I1 is equal to 0. Now I1, I2, and I3 are all given, so I can plug them in. And this problem is very clever in that it doesn't entangle the equations for A and B. So you only have one equation and one unknown each, so that should make things simpler. So minus B, because I1, well, I won't even bother with this simplified form. I3 minus I2 is minus 1 minus plus 1.5, which is minus 1/2. So minus 0.5 is equal to B times IB, which is I1 minus I3, which is 3. So then B is equal to minus 1/6. Okay. And then for A, minus 10, A plus 1, plus 10, A plus 1 times minus 1.5, plus 40 times minus 3 is minus 80, equals 0. You know, it would probably have been better if I just used the top line. I don't know why I did all these unnecessary steps. They're going to stay in the video, but they're unnecessary. So minus 60 minus A times VA, which is equal to 10I1 minus I2, which is 10 times 2.5, which is 25. So 25 plus 10I3, which is equal to minus 20, right? Because I3 is minus 2, plus 5, plus 10I2 minus I1. I2 minus I1 is minus 2.5, so that's minus 2.5. But there's no point because there's a times 10. Equals 0. So minus 60 minus 40 more is minus A25 is equal to 0. So A is equal to minus 1/4. Let me look at that one more time. So minus 60 minus A times 10 times I1 minus I2, which is 2.5, so minus A times 225, plus minus 20 plus 5 plus 10 times, and the same thing switch, so minus 2.5, which is minus 25. This is minus 40 here. It's minus 60. So you get minus 100. Move to the other side. It's plus 100 divided by minus 25. And get minus 4 instead of minus 1/4. Minus 4. Okay. Now, these don't have units because these are current-controlled current source and a voltage-controlled voltage source. So the gains are unitless. Hopefully I didn't make a dumb mistake in there anywhere. Okay, next problem. So at least this one I specify the current dependence. Define my mesh currents. So I1 is equal to 2 amps because it's given. 1 I2 minus I1 plus 1 I2 plus 1 I2 minus I3 equals 0. So that would be 3 I2 minus I1 minus I3 equals 0. And then lastly, I3 is equal to 4 IA, which is equal to I1 minus I2. This current source is hanging out on the outside, so it's going to determine what this mesh current is. It doesn't matter what this voltage source says. It doesn't matter if there's a resistor here. They don't contribute anything to what the mesh currents are. So then I can just plug in this I1 equals 2. So I get 3I2 minus I3 is equal to 2. And 4I2 plus I3 is equal to 8. Easy elimination here. 7I2 is equal to 10. I2 is equal to 10 sevenths. I3 is equal to 40 sevenths with a minus sign plus 56 sevenths, which is equal to 16 sevenths. And these will be amps. Always put units on your stuff. So plug those in and check. So minus 2 plus 3 times 16 over 7 minus 10 over 7 is equal to minus 14 sevenths plus 48 sevenths minus 10 sevenths, which is not 0. So there's a mistake in here somewhere. Right, so 30. Yeah, the mistake isn't checking it. I mixed up I2 and I3. That's fine. Okay. And then this one, 16 over 7 is equal to 4. 2 minus 10 over 7, which is equal to 16 over 7 is equal to 4 times 4 over 7. So that checks too. So these both. So that all checks. So there's most likely not a mistake in there. On to the next problem. Looks exactly the same as the previous one, except that now I have an independent voltage source. So again, I1, I2, I3. I1 is still 2 amps. I2 minus I1 plus I2 plus I2 minus I3 equals 0. So 3 I2 minus I3 equals 2 is still the case. And then we have this last one here. So 1 I3 minus I2 minus 4IA, which is I1 minus I2, plus I3 plus 6 equals 0. Making it a voltage source makes this more complicated, but we still two equations and two unknowns. We just plug in 2 for I1. So this is I3 minus I2 plus minus 8 plus 4I2 plus I3 plus 6 equals 0. So this is 2. My I2 terms are 3. So 3I2. And then for I3, I have 2 I3s. I have an easy elimination going here. I just subtract. So minus 3I3 equals 0, which implies that I3 equals 0, which implies that I2 is equal to 3 halves. So or 2/3. I3 is equal to 2/3. If we can make sure that makes sense, we have 2/3 minus 8 plus 6 plus 4/3 8/3. Oh dear. Something seems fishy about this. Okay, it's supposed to be a minus here because it's a minus, and that makes us all add to 0, and that checks. So it's amps, that's amps, and there you go. We got to make sure that this makes sense conceptually, because I noticed that one of the currents turned out to be 0. So why would it be 0? And the answer would be, well, these voltages would cancel each other out. So what's the voltage? Well, no, because you could still have driving. Let's see, what is this voltage though? So IA is I1 minus I2, which is 6/3 minus 2/3, which is 4/3. So IA is 4/3. And so this right here is 16/3 of a volt. And this voltage right here is just I2 minus I3, which is 2/3. So we have 2/3 going up. We have 16/3 going up some more. So that would be 18/3. So from there to there is 6 volts. So there's no voltage across this resistor because it's 6 volts on both sides. So there's no current going through. Okay. And that's all the problems. I'm going to zoom out, and though not as nice looking as the node voltage sheets, I'll still pan through the sheets. So this is the first one. Oops. Second one. Third one. Fourth one. Fifth one. Sixth one. And the seventh one. Okay, a lot sloppier, a lot more stupid mistakes than node voltage. That's just how it goes, you know. I don't have any issue conceptually understanding things. However, I'll just like start writing and talking and have no idea what I just wrote. So I'll think one thing and my hands will just randomly write another thing. But anyway, that was that. I won't talk about the hierarchy of circuit solving techniques in detail until I do an aggregate of multiple different circuit solving problems using the entire library of resistive network techniques. So eventually I'll get to that. So that would be node voltage, mesh current, using source transformations, reducing parts of a circuit into their Thevenin or Norton equivalents, and using the principle of superposition. Until then, this is over.